Assalamu alaikum and welcome. A very good evening to all of you. My dear students, this is one of the most informative and easiest videos on my YouTube channel in the playlist Advanced Microeconomic Theory. So in order to understand this, kindly watch this video till the end so that you could understand the concept. Andrew Carter of the New York University remarked very nicely in his book on microeconomics, a modern approach, that demand curves are not dropped from heaven upon individuals, but rather they are the result of their attempts to maximize their utility given their incomes. Specifically, let us assume that the utility function be defined over the consumption of n amount x1 of good 1 and n amount x2 of good 2, and let W be the income or budget of the individual that he can consume on the two goods x1 and x2, and let us assume that P1 and P2 be the prices of goods 1 and 2 respectively. The budget constraint for this problem is given by this equation, where W is equal to P1 x1 plus P2 x2, where P1 x1 is the share of income spent on good 1 and P2 x2 is the share of income spent on good 2, and the sum of the two should be equal to the budget or income at the disposal of the consumer. The individual's problem is to choose the quantities x1 and x2 given her income W and prices P1 and P2 to maximize utility U function of x1, x2 subject to the budget constraint. So this is his problem. More formally, the problem can be written as maximize utility from x1, x2 by choosing x1 and x2 amounts of good 1 and x2 subject to the budget constraint given by W is equal to P1 x1 plus P2 x2. So this is the utility maximization constraint utility maximization problem of our agent subject to the budget constraint. Now we may define the problem which is known as Lagrangian problem, and this problem combines the utility function and the constraint of the problem as follows. So the Lagrangian function or the Lagrangian expression L as a function of x1, x2 and lambda is equal to the utility function u of x1, x2 plus lambda into the budget constraint, where the budget constraint is W minus P1 x1 minus, this should be minus P2 x2, this should be minus. So this is the Lagrangian expression, and then we can maximize the Lagrangian with respect to x1 and x1, x2 and lambda, and the first order of necessary condition yields the following system of equations. So partial of the Lagrangian with respect to x1 is equal to partial of the utility with respect to x1 minus lambda P1 is equal to 0. Similarly, partial of the Lagrangian with respect to x2 is equal to this statement, and that is equal to 0. And finally, the partial of the Lagrangian with respect to lambda, which is the Lagrangian multiplier, is equal to the budget constraint, which is given by this equation. This system of equations can be solved for the equilibrium demand functions x1, x2 and the equilibrium level of lambda, which is the marginal utility of income, and solving these three equations simultaneously will give us the following equations. So x1 star is the Marshallian demand for good 1, which is a function of income, price of good 1 and price of 2. Similarly, the Marshallian demand function or curve for good 2 is given by x2 as a function of W, P1 and P2, and similarly the Lagrangian, the optimal value or the equilibrium value of the Lagrangian multiplier lambda is equal to lambda as function of income, price of good 1 and price of good 2. And as I mentioned, x1 star and x2 star are both functions of W, that is the consumer income or budget, price of good 1 P1 and price of good 2 P2, and these are the equilibrium demand functions. These are also known as the Marshallian demand functions for good 1 and good 2. Now consider we may discuss an explicit example. Let us suppose the utility function is multiplicative, and that is this multiplicative utility function is given by x1 times x2. Now, setting up the Lagrangian expression, we may write this as L as function of x1 x2 lambda, and that is equal to x1 x2. This is the multiplicative utility function time plus lambda times W minus P1 x1. This is also minus P2 x2. Sorry for this. This is a typo. So this should be W minus P1 x1 minus P2 x2. And the maximization problem then reduces to this, that is maximize x1 x2 by choosing quantities of good 1 and x2 plus lambda, and this is the budget constraint. So the first order conditions are here. This is the partial of L with respect to x1, and this is the partial of the Lagrangian expression, the Lagrangian function with respect to x2, and this is the partial derivative of Lagrangian function with respect to lambda. So from this we get that W is equal to P1 x1 plus P2 times x2, and from equation number 1 we get that x2 is equal to lambda times P1, and from equation number 2 we get x1 is equal to lambda times P2, and if we substitute for x1 and x2 in the budget constraint, then we can write budget constraint like this. So lambda is equal to W, which is budget or income of the consumer, divided by 2 P1 P2. So lambda is a function of income of the consumer as well as the price 1 and price 2, that is prices of the two goods. Similarly, x1 star is equal to W divided by 2 P1. So this is a function of the consumer income and own price. Similarly, x2 star is also equal to W divided by 2 P2. That is also a function of income and the good 2 price. These x1 star and x2 star are the Walrasian demand functions or Marshallian demand functions. These are also known as ordinary demand functions or curves. We may note that both the demand curves are downward sloping, in fact, but how we can prove that they are downward sloping? So from the previous page, that is from here, if you take the partial of this x1 star with respect to P1, and if you take partial of x2 with respect to P2, then we may prove that these must be downward sloping. So here is the partial derivative of x1 with respect to P1, and that is equal to minus W by 2 times 1 divided by P1 square. Since the sign is negative, so that is less than 0, and this means that the rate of change of the curve or the demand function for good 1 with respect to its own price is negatively sloped. Similarly, curly x2 divided by curly P2, that is partial of x2 with respect to P2, is also negatively sloped because the sign of this derivative is minus, and that is negative less than 0. So this means that the demand curve for x1 with respect to its own price and the demand curve for good 2 with respect to its own price both are negatively sloped. So this is the mathematical proof of how we can say that the demand curves are negatively sloped. Now we can also show that the price elasticity of the demand is constant, and that is equal to 1. So how can we prove that? Let us start with the definition of the elasticity. So this is the elasticity, own price elasticity for the good one, and this says that that is equal to the ratio of the partial derivative of x1 with respect to p1 divided by x1 divided by p1. And if we simplify that, then we finally have that it is equal to -1. So in absolute term, the own price elasticity of demand for good one is equal to 1. Similarly, this would also be equal to 1 for good 2 in the same fashion. So as I said that symmetrically for x2, we have also that the own price elasticity of demand, that is psi2 is equal to -1, and in absolute term it's equal to 1. So the own price elasticities of demand for good 1 and good 2 are unitary elastic, that is equal to 1. Finally, we may also compute the equilibrium level of utility, and that is obtainable by substituting the equilibrium values or the optimal values of x1 or x2, or in other words, by substituting the Marshallian demand function in the utility function, in the original utility function, which is given by the following equation. So we may show that by u star, that is the optimal utility or the equilibrium level of utility, and instead of x1 x2 we write Marshallian demand function, and Marshallian demand function for x1 or good 1 and Marshallian demand for good 2. And we knew in the previous slide that the Marshallian demand for x1 star is equal to w divided by 2p1, and the Marshallian demand function for good 2 is equal to w divided by 2p2, and if we simplify, finally we have 1 by 4 times w square p1 p2. So this is the maximum utility which the consumer can attain subject to the budget constraint. So this is I hope this is very informative and easy for you to prove that the demand curve with respect to own price, the demand curve for a commodity is negatively sloped, and this is the mathematical proof for good 1, this is the mathematical proof for good 2, and then we proved that the elasticity, own price elasticity of demand for good 1 is equal to 1, that is in absolute if we ignore the minus sign. Since the demand curve is negatively sloped, so this negative means that there is a negative relationship between the percentage change in quantity and percentage change in price. They move in opposite direction, so that is why this sign is negative. So in absolute term, this own price elasticity of demand is equal to 1. Symmetrically for x2, this is also equal to 1. And finally, by substituting the values of Marshallian demand function for x1 and x2, we get that the maximum amount of utility that this consumer or this agent can attain subject to the budget constraint that he faces by given level of income and the given prices of the two goods. I hope this is informative and easy for you to understand. If you haven't yet subscribed to this channel, kindly subscribe to the channel, and don't forget to click on the bell icon so that you can get regular notifications about my videos that I'm going to upload for you soon. Kindly share various videos of this channel in various WhatsApp groups so that these could reach to the maximum possible number of people. Thank you, and see you again.